Hello everyone and welcome back. Today we are going to take a closer look at velocity versus time graphs. And we're going to answer a few questions that are very common in assessments and standardized tests. So let's start with this graph. So here's a velocity versus time graph of an object that is moving left and right. To start out, let's begin with some very basic understanding. For each section of this graph, is the object moving right, left, or stopped? And is its velocity increasing, decreasing, or constant? To start, let me label these sections so I can easily identify them. A, B, C, D, E, and F. A, B, C, D, E, and F. And as usual, it may be a good idea to pause the video and answer these for yourself before we get going. To start out, since the y-axis itself is velocity, and the data starts out at -15, that means whatever this object is moving to the left at 15 meters a second right when the clock starts. Looking at this first section A, it is moving to the left at 50 meters a second, and that velocity is not changing. So for A, we have to the left and constant velocity. B, this data is still in the negative, which means it is still moving to the left, and the data is getting closer to 0. So we have a decrease in velocity. In other words, it is slowing down. At C, we have 0 velocity, so it is stopped, and is staying at 0 velocity, so this is still considered to be a constant velocity. For D, we have our velocity now in the positive, so it is definitely moving to the right, and that velocity is increasing, it is getting farther away from 0, so we have an increase in velocity here. For E, we are at the positive 15 meters a second, and that velocity is not changing during that time period, so it is moving to the right, and we have a constant velocity. For F, we have something interesting. It starts out at positive 15, then slows down to 0. So I'll call this F part 1 is moving to the right and is a decrease in velocity. However, I'll call this part here F part 2 because it starts at rest and begins moving to the left. And the velocity is getting farther from 0, so that velocity is increasing. Now, while we're here, there's something I want you to look at that has a very close relationship to what we just did. At point A, I have a negative velocity and 0 acceleration, so the velocity is not changing. For B, I have a negative velocity and I have a positive acceleration, which means the object's slowing down. For C, I have a 0 velocity and 0 acceleration. For D, I have a positive velocity and a positive acceleration. Since they're both positive, the object is speeding up. For E, I have a positive velocity and 0 acceleration, so the velocity is not changing. For F1, I have a positive velocity and negative acceleration. Since the velocity and acceleration are in opposite directions, the object is slowing down, just like for B. For F2, I have a negative velocity and a negative acceleration. So since these two signs are the same direction, the object is speeding up in the negative direction. So before you actually get into real details, having a good understanding of these concepts are really key, and very good base questions to ask yourself. Is it moving left, right, or stopped? Is it speeding up, slowing down, or is the velocity constant? And you can match that understanding with what I just did with the signs. Is the velocity positive, negative, or 0? And is the acceleration positive, negative, or 0? Speaking of acceleration, that's our next question. What is the acceleration for each section? So to start, let's bust out our acceleration formula, which is acceleration is change in velocity over time, which is Vf minus Vi over delta t. I will keep the same section labels to avoid confusion. So for A, we have no change in velocity here. So the numerator here is 0, and a constant velocity means no acceleration. For B, we have a change in velocity from -15 to 0, which is positive 15 meters per second. If you did Vf minus Vi, it'd be 0 minus -15. Over, we go from 4 to 6, 2 seconds. Gives us an acceleration of positive 7.5 meters per second squared. For C, the object is stopped, it is not changing velocity at all, so again, no acceleration. For D, we have a change in velocity from 0 to 15, so positive 15 meters per second. Over, we go from 8 to 12 seconds, 4 seconds, which gives us an acceleration of positive 3.75 meters per second squared. For E, we have a constant velocity of 15 meters a second, so again, we have no acceleration here. Now, F1 and F2. For a velocity versus time graph, acceleration is represented by the slope of the line. So F1 and F2 actually have the same acceleration. I'm not going to bother getting them in pieces, because I know it starts at 15 meters a second and ends at negative 5 meters a second. So my change in velocity, Vf minus Vi, is going to be negative 5 meters per second minus positive 15 meters per second over 14 to 18 is 4 seconds, which gives me negative 20 meters a second over 4 seconds, which gives me an acceleration of negative 5 meters per second squared. So here are our accelerations with the non-zero accelerations being boxed. And notice the first part of F, it's slowing down because the velocity is positive, but acceleration is negative. The second part is speeding up because the velocity is negative and the acceleration is negative as well. Now for this last question, what is the instantaneous acceleration at 5.39 seconds? This is a very specific time point here. 5.39 seconds is about here, which is about here. Now, just like we did for instantaneous velocity on the position versus time graphs, you don't really care about that point exactly. You need to have a good idea where it is, only that's all you need to know. Because what you want is the slope. And the slope at this one point is the same as the slope of this entire line. And we already have the slope of that entire line. It is right here. So the instantaneous acceleration at 5.39 seconds is going to be positive 7.5 meters per second squared. That is also going to be the acceleration at 4.2, 4.3, 4.4, or 4.5 seconds, anywhere between 4 and 6 seconds, because the slope is not changing between those 2 points. All right, let's talk about one more question. The other type of question that is very common is, what is the displacement? You can very easily get the displacement of an object off a velocity versus time graph. We have already discussed this, and there are 2 ways to do it. So to start out, what is the displacement of the object from 0 to 4 seconds? One way to get the displacement off a velocity versus time graph is to get the area under the curve. So to get the area of this rectangle, I would do height times base. The height is negative 15 meters per second. The base is 4 seconds. I do this, seconds cancel, and I would get a displacement of negative 60 meters. Something to keep in mind, what we just did was velocity average times time gets us displacement, which is just our average velocity formula rearranged. How about from 0 to 6 seconds? Well, we already have the area from 0 to 4. Now we just need to add the area from 4 to 6. And since it's a triangle, the area of a triangle is 1/2 height times base. So 1/2, the height again is negative 15 meters per second. The base this time is 4 to 6 seconds, which is 2 seconds. These seconds cancel, and actually these 2's cancel, which gives me a displacement of negative 15 meters. But this is just the displacement from 4 to 6 seconds. The displacement from 0 to 6 seconds, I need to add what I have up here, which means the actual answer here from 0 to 6 seconds would be these 2 areas combined, which would be negative 75 meters. Now let's do the one that's a little tricky. What's the displacement from 14 to 18 seconds? Again, there's 2 ways to do this. If I wanted to, I could get this positive displacement and this negative displacement and combine them to get the total displacement from 14 to 18 seconds. But considering how cleanly this data comes out, I'm going to use something else that's in our arsenal. I'm going to use the first kinematic equation straight out. A graph is basically like givens. It tells you exactly what you need. From 14 to 18 seconds, Vi is positive 15 meters per second. Vf is negative 5 meters per second. Time from 14 to 18 is 4 seconds. Keep in mind what I just underlined is average velocity. I'll get that first. 1/2 15 meters a second plus a negative 5 meters per second times 4 seconds. 15 minus 5 is 10 divided by 2. So the average velocity is 5 meters per second times 4 seconds. My seconds now cancel, and I get a displacement of 20 meters. So that means between 14 and 18 seconds, this object is first moving to the right, slows down, stops, then speeds up moving to the left. So if I could borrow the space, it is something like this. You're moving to the right, slow down, stop, move to the left, and then the data ends here. Their displacement from start to finish is still positive. And that's why we get positive 20 meters as our answer. So for velocity versus time graphs, things you need to know: basic understanding, left, right, speeding up, slowing down, how to get the acceleration, which is the slope of a line, very important, how to get the displacement, which is the area under the curve. All right, I will end this here. Have a good day. This is Mr. M signing off.